So welcome to this first of what will be 3 lectures on quantum channels. Okay, this first lecture concerns effectively a derivation of the Lindblad master equation that you also saw in the seminars of Danny, but from a completely different perspective. Okay, so in Danny's lectures you had a microscopic derivation, a very physical derivation. Here there will be very little physics. Here we're going to derive it from a completely functional analytic way. Okay? The main reference for this first part of the lecture are these 2 seminal papers. They came out the same year. I will mostly follow the derivation in this first paper, which is by Gorini, Kossakowski, and Sudarshan. The second paper is by Lindblad. Okay? But it's effectively the same derivation. Okay? Now, before I do so, as it's going to be very mathematical, we need to establish kind of a common ground. So we need to have a primer on what's known as functional analysis. Okay, so I'll start from the very, very beginning with the definition of what is a normed vector space. Okay. So for the first part, I will denote vector spaces by capital letters. Later on, I will switch a little bit the notation, but you'll see why, because we'll make it more, look a little bit more like quantum mechanics. So let X be a vector space over a field F. Most of the times we take this field to be the real numbers or the complex numbers, but it could be any field you want. Okay? Yes. This is the first identity. This is the second identity. Okay? And finally, we need to have a triangle inequality. Then we say that this pair, X, this is normally called the norm of the vector space. So X equipped with this norm is called a normed vector space. Okay? Yes?
Where it reads X, let X be a vector, is X be a vector space?
Sorry?
Let X be a vector space, right?
Yes. Thank you. Yes, please correct me. I might be missing words or changing notation, so if you spot something, please let me know. Okay, so that's the first definition. The second definition is the concept of a Cauchy sequence. Okay. So from now on I'm going to write this, meaning a normed vector space, right? So k is a positive integer. Okay? Which is the notion that as the sequence gets longer and longer and longer, the difference in norm between the elements of the sequence gets smaller and smaller and smaller. Okay? This is a fancy way of saying a convergent sequence. Okay? So with these two definitions, we can now define what is a Banach space. Okay, so a Banach space is we have a normed vector space. I'll say it in words before I write. Essentially, a Banach space is a normed vector space that is complete in its norm, meaning that every Cauchy sequence converges to some element which is in the vector space. Okay? So, okay, so it's a Cauchy sequence and its limit point is in X. Okay, now just to give you a bit of context, this is because this may seem very abstract. Every finite dimensional vector space over the reals or over the complex numbers is a Banach space. Okay, because it's under any norm. You can pick any norm you want. Okay. Another Banach space, and this is the one that we are going to use. Let's call it quantum mechanical examples. Let me see how I defined it. Yes. So the bounded operators. Actually, I don't need it actually here. H, this is the set of all A, that map H to H, such that the norm of A Okay? This is known as the set of bounded operators on the Hilbert space, bounded because the norm is defined as the operator norm. Okay? This is a Banach space of all bounded operators on a Hilbert space. Okay? Notice that this Hilbert space can even be infinite if you want. Okay? And the norm of the space is the operator norm. Okay? There is another set that I'm only mentioning because you might need it if you ever do quantum mechanics over infinite dimensional Hilbert space. And this space is all A from H to H, such that okay, this SH is known as a Banach space of trace class operators. Why trace class? Because the norm is the trace norm. Okay? Notice that this space is a subspace of this space. Right? Because if your operator norm is bounded, that is the maximum eigenvalue is bounded, then, and since it's less than infinity, the trace is also bounded, so this belongs in that one, but not the other way around. Okay? Yes?
Sorry, you might have said this already, but you're taking the supremum over all vectors x with norm 1?
Yes.
Okay.
Yes. Exactly. Okay, however, I only made this distinction now, but for the rest of this lecture, what we're going to be concerned with is finite dimensional Hilbert spaces, which means that the bounded operators also form a finite dimensional subspace. If the subspace is finite dimensional, these two spaces are isomorphic. Can everyone see why? No? If this is finite dimensional, this basically says that the maximum eigenvalue is bounded. There's only a finite number of eigenvalues, so if I take the trace, this is also bounded, and I can associate it to a trace class. Okay? Good? Okay, so okay, there are subtleties when we go to infinite dimensions, but everything I'm going to talk about now is finite dimensional Hilbert spaces. Okay, now comes a very important notion, and that is what is known as the dual space of functionals. Okay? So let X, the normed vector space, be a Banach space. Over some field. The dual space of functionals. Normally we just put an asterisk over the vector space. It's essentially the space of all functions that take elements from the vector space into the field. Okay? And it needs to satisfy the following two properties. The first one is linearity. So for all this is true. And the second one is that there exists a constant bigger than 0 right? So whatever the norm is on x, this functional on x can only increase the norm by a very bounded number, okay? Now there's an important remark here. That this dual space is also a Banach space under the operator norm. And this norm is defined as the sup of this. Okay? What are these dual spaces in quantum theory? Okay, so in quantum theory, the objects of interest are always positive, semi-definite operators with bounded trace. Okay? And since the trace is bounded, we can always choose it to be 1. Okay? Maybe I should say this is equal to the trace okay? Notice that the positive operators are a subspace of the Banach space, okay? And they're also a subspace of this space. Everyone can see why this is not the full space? There's nothing about positivity here, okay? So you can have non-positive operators that have a bounded trace. So if the operators are in addition impose positivity, these form a subspace of this one, and since infinite dimensional Hilbert spaces, these two are equivalent, they're also a subspace of the one above, okay? Good. On the other hand, in quantum mechanics, we also have observables. Okay? And observables are simply bounded operators. They're also Hermitian. Okay, so they belong in this space as well. The only thing missing is the linear functional. So what is the linear functional in quantum theory? Well, when you compute the expected value of any operator, what you do is this. Correct? So the linear functional, or the space of linear functionals, is this one. Okay? And notice that this forms a Banach space. So what you have in general, okay, the dual space of the trace class operators is the bounded space of Hilbert, of operators on the Hilbert space. Since we are in a finite dimensional space, we said this without the asterisk is the same as that. So the dual space of a Banach space of finite dimensions is the Banach space. Okay? You might be more familiar. You effectively do this. Let me give you an example with Hilbert spaces. So a Hilbert space is a normed vector space complete in its norm. So it's a Banach space, right? Let's take it to be finite dimensional. And the objects you write like this. What is the dual space? Well, the dual space is the space of all bras. In the finite dimensional space, this is the same thing as the Hilbert space. So it's all these guys. And the linear functional on psi is simply this. Okay? So it's just fancy language to say all this. The deeper relation of these Banach spaces and dual spaces is the following. If you work with the Banach space, you are working in the Schrödinger picture. You are dealing with how these objects evolve. When you're working in the dual space, you're working in the Heisenberg picture. You are asking yourself how these objects evolve, okay? And the connection between the Schrödinger picture and the Heisenberg picture is this one, okay? All this language essentially says this, okay? Clear? Good. So now that we have all this language sorted, let's start doing, yes?
That correspondence is guaranteed, right? And there is here.
Yes, that is that correspondence. There you go, you got it in, yes. This is the Rietz theorem, okay? Formally, mathematically, the correspondence is to the Rietz theorem. Okay? So let me just for completeness, let me write it here. So here you have the Schrödinger view. What you're doing is you're working with SH. Then there's the Heisenberg view. Actually, I should say maybe I put a plus here to denote that they are the positive operators in SH, which are a subspace of this guy. The Heisenberg view is you're working with the Banach space. And the connection between these two are the linear functionals. Okay? And I misspelled view. Okay? Good. Now that we have all the spaces sorted out, the next obvious question is, we've defined the space where objects live. We've defined the dual space on how to get from those objects to the field. The next logical question is, how do I move from an object in the space to another object in the space? Or to an object in a different space? Okay? So the next thing that we're going to do is define the linear operators.
Can you say Schrödinger and Heisenberg both like norms, but they couldn't agree on which one we wanted?
Sorry?
It seems they like norms, but the difference is which norm they like.
Correct. Yes. But you can't blame them because, I mean, I don't think either one of them knew this functional analysis and Banach spaces and all this stuff. So it's this came much later. So now we need the concept of a linear operator. I will drop now the norm notation and just simply write okay, X and Y are two Banach spaces. I'm going to use E for a map for a reason, because we're doing all this to discuss quantum channels. Typically, quantum channels are represented by the Greek capital letter E. Okay? This you should all know, I guess. Where did I? This doesn't say anything about the operator being bounded, so we need to define what a bounded linear operator is. E is bounded. Sometimes in the literature you may see people write continuous. Okay? If there exists a constant bigger than 0, such that so the idea is, remember, E maps X to Y. So if I compute the norm of the output of the linear map according to the norm of the Banach space Y, this cannot be bigger than a constant times the norm of my original vector, where the norm is taken over the Banach space X. Okay, this is what this notation means. Okay, oftentimes the norm is always the same because the space is always the same, but in general, this is the definition. Okay, and this is for all X and X. With this, you can also define the operator norm of bounded operators. I'll skip the linear, I'll just write operators. I mean linear operators, okay? So again, the operator norm this is the sup. Since the input is the Banach space X, we have to take the sup over the operator norm of that space. And the output is the operator norm of the Y space.
Should that be an E instead of a T?
C, yes, sorry. It's because in my notes I used T and then I regretted it this morning. Okay? You might be wondering, why do we need to define a bounded linear operator? The reason is that a linear operator between Banach spaces is continuous if and only if it is bounded. Okay? So, all this, because remember our goal is to define transformations, okay, general transformations of states to other states. These are going to be obviously bounded linear operators, but it won't be one bounded linear operators. It's going to be a family of bounded linear operators, right? Particularly if we're considering a time evolution, there is a parameter called t, and for every t, we're going to have to ensure that the operator is bounded and continuous and all these things and so on, okay? So, to do that, in quantum theory, this one parameter family, particularly when we're dealing with density matrices, is associated to a very important concept called a semi-group, okay? If we were talking about unitary evolution, then it will be a full group. In other words, you can go forwards, but you can also go backwards to the beginning. A semi-group is, you can go forwards, you can't go backwards. Okay? So, we need to define a parametrized family. I'm going to give it as a general definition, okay? It could be multiple parameters. It doesn't have to be one. It could be 2, 3, 5, m parameters, okay? Okay. And E. Okay, just a very simple definition. Now, this is general. From now on, this set theta is going to be this. Actually, be more precise, this. Okay? Before I define what is a semigroup, I need two more properties. Okay? And these have to do with the concept of weak and strong continuity. So, again, we have two Banach spaces. And we have now a one parameter family. Okay? Sorry, for all x in x, put it in physical terms, remember, these are the functionals. So a linear map is weakly continuous if it converges on the average, right? Remember, this is the trace of an operator with a state. So we say it's weakly continuous if the average values are continuous, okay? The underlying state, in other words, the evolution of the actual state underneath need not be continuous, okay? So long as the average is continuous. So you may have guessed that it's strongly continuous if this is true. Okay? So weak continuity is the average, the expectation values are continuous. Strong continuity is the underlying states with which you produce these expectation values are continuous. Okay? And with these two, we get to the crux of the problem. What is a semigroup? So again, we have two Banach spaces, and we have a one-parameter family of maps. Okay? Remember, this theta is this one here. The first property is that if theta is 0, this is the identity. Okay? This here means composition. Okay? So if I first do this map and then do this map, it is the same as if I did this map from this family. Okay? This is very important. Okay? Actually, there is a lot of physics hidden in this assumption here, because if you remember from Danny's notes, this is effectively the Markovian property. Okay, so I demand that this is true for any theta bigger than phi. Okay? There is often an optional requirement. Yes?
Why do you demand the condition of strongly continuous?
Why do you demand a strongly continuous condition for a semigroup? I think this has to do with proper taking limits, right? Because you might not have, this might not be enough to actually do the transformation. Let me put it this way. If you demand this, this is automatically satisfied. If you demand this, this is not automatically satisfied. And you want it on the state. Okay? There is often one additional condition. I'm only mentioning it because I'm going to quote a theorem which uses it. And this condition is that the norm, or the operator norm of this, Okay, this is normally known as the contraction. In other words, that the operator norm of this doesn't blow up too much. Okay. Now,
sorry, can we go back a second? Why did we require that theta is bigger than phi in property 2?
Because this means that going this way is okay, going this way, not okay. That's the semigroup property. So phi has to be smaller than theta, right? So the idea is, imagine that you want to go to time 10.
Yeah.
Okay, and what this is telling you is, if you evolve directly to E10, it's the same as if you first evolved for 2 seconds and then evolved for 8 seconds.
But couldn't we also evolve for 8 seconds and then evolve for 2 seconds? You know, why is that a requirement?
Sorry. Yeah, sorry. You're right. Yeah, you're right.
So they
I think
just
so.
both be greater than 0.
Yes, both of them be greater than 0. You are correct. You are correct. Yes. Okay. Now, all this to basically tell you the following. If you remember, when we were dealing with unitary dynamics, we had a theorem, okay, called Stone's theorem. That says that every unitary operator can be written as e to the minus I, some Hermitian operator. Right? This is always true. So all this now definition is that to write down the analogous statement, but for general semigroup dynamics. Okay? So there's a theorem. I won't prove it. Called the Yoshida theorem. Okay? That basically tells you that now I'll put time here because we're going to be dealing with time evolution. Okay? The theorem is a bit more subtle. Okay? There is a few conditions that this L operator has to satisfy. In particular, it has to be dense in X. Okay? There's some conditions on the spectrum of it, but I don't want to, we're already over time. I don't want to bore you with it. If you want to learn more, you can look it up in a book or in Wikipedia. It has a very good exposition of it. Okay? But the important thing is that if you have a one parameter family that forms a semigroup, okay? We should say this, where okay? So if you have a semigroup family, then there's, under certain conditions, let's call them regularity conditions, you can always, there exists some linear operator that generates the semigroup. Okay? In other words, you have it like this. Okay? This is the analog of Stone's theorem, but for semigroups. Okay? Good. Any questions so far? Sorry, this is brutal, but necessary. Okay? So far it's just definitions, everyone understands? Good. And the next part is where it's the only part in the original papers where I could identify physics. Okay? is that we're going to need one more concept which mathematicians can define it, but for no apparent reason. Here, you need it for physical reason, okay? And that concept has to do with positivity and complete positivity, okay? Oops, no, that's correct. Actually, I'm going to define 3 concepts, okay? So, all of them start like this. We said that E is positive. Okay? We see that E is hermeticity preserving. If the following is true, okay? And this is the tricky one. Okay, it's complete positivity. Maybe I should call this XY. Let's call it W. So it's completely positive if I introduce an auxiliary Banach space of some dimension n, and if I consider now this linear transformation, this is positive for all n. Okay? If we're dealing with Banach, finite dimensional Banach spaces, it suffices to check for only one n, which is the dimension of the Banach space. The reason being, for any n smaller than that, I can always append zeros and make it the full dimension, so I only have to check here. Okay? What is the physical reason why we demand this complete positivity? The physical reason is the following. So you know that in quantum mechanics, if I have any positive operator, okay, I can always diagonalize it, no? So this is by the spectral theorem. I can always write rho like this, yes? These are the eigenvalues and these are the eigenvectors. Okay? I can also write rho as the trace over a purification. In other words, now let so this is my original system, my original Hilbert space, and this is some auxiliary Hilbert space of the same dimension. Consider now this bipartite state. Then it's trivial to show that if I trace out the auxiliary system from this state, I get rho. Okay? Now, oftentimes you're taught this as a trick. It's just a trick. You can always introduce some fictitious system, and you can think of essentially your mixed state here. The mixedness comes from the fact that actually your state is entangled with some other reference system that you do not have access to, and you only see the system locally. But this can be, it's a physical thing. Your system could, in principle, be entangled with something very, very far away. And if you do things on your system, right, the whole thing with the system far away should be a valid quantum state. This captures this property, right? This is your system. This is the auxiliary system from the purification. If you do something locally, the result should also be a positive operator, okay? That's the content. So you need this. If this were not true, I can construct a superluminal signaling scenario, right? So imagine I give you an evolution for which this isn't positive, which means that I sit here, I do this evolution for which this is not positive. My friend on the other side, if the resulting state is not valid, his measurement is going to give him error, right? So I tell him, okay, if I do something legal, I send you 0. If I do something illegal, you'll get error, it's like 1. So I can use it to superluminally signal. As soon as I do it, he will get an error on the other side, and I can communicate faster than the speed of light. Okay? So this part is crucial, okay? And with this, we are ready to start with the Gorini, Kossakowski, Sudarshan derivation. How long do we have? It's already been an hour. Okay, I'm going to try and go very, very, very fast. Okay? So with all this, all that is left to do is essentially derive the general form of this generator here, right? We have a semigroup. We know it can be written like this. The question is, if we demand complete positivity, what is the most general form that this operator can have? Okay? So let's start with that. Some proofs which are obvious I might skip for the sake of brevity. The first one is a necessary and sufficient condition for any operator L, or rather for any semigroup, to be completely positive. Okay? So, we'll assume the Hille-Yoshida form. Now instead of writing X, I'm going to be writing bounded operators on a Hilbert space, and this Hilbert space will be of dimension n. Okay? I'm going to add an additional word here. Dynamical here means the following two things. Okay? So far I'm only asking for positivity and trace conservation. Okay? We're also going to define a set of projectors. So you should recognize this as a complete set of projectors, right? They're Hermitian, they're pairwise orthogonal, they sum up to the identity. That's why I wrote them like this. Okay? And this is the important part. So L can be a generator of this dynamical semigroup if and only if the first condition says the trace notice that this condition is equivalent to this condition. Let me go ahead and write it like this already. Okay? And the second condition is that the trace of pk this is positivity. Okay? So this part is essentially this part, and this part is essentially this part. Okay? Proof. So, by virtue of it being a dynamical map, it must be that this is true. Okay? But the second property of the semigroup is I can go to the total time t in n infinitesimal steps, each of which is t over n. Okay? And by strong continuity, I know that if I take the limit of these small infinitesimal steps to 0, right? This must be 0. Right? Which means that if I use the Hiei-Yoshida, I can do a Taylor expansion of this guy up to second order in delta t. Right? This will be the identity. Okay? So, that 1 and 2 are necessary follows from the fact that 1 is equal to the trace. Since these are rank 1 operators, right? I can choose my initial state to be one of these guys. Which is equal to the trace of this guy, which is equal to the trace of, we have PL plus delta TL of PL plus something which is delta T squared, right? Now I use this correspondence, that this is equal to the sum over K, the trace PK multiplied by PL plus I have this. These are by definition orthogonal. And it's only 1 when K equals PL. So this is 1 plus this guy. And if I want it to be equal to 1, it must be that this guy has to be 0. Right? There's a sum here. Yes? The second property is that we also, if it's a dynamical map, we know that this has to be equal to 0, right? Okay, which implies that if I take, this is essentially this condition, let me put here delta t. Okay? Now what I'll do is I'll choose the state to be some projector from that set. Since that set is complete, I can also write phi in that sense, right? Which means that I can write this These are positive because rho is positive, right? So I only need to prove that this guy has to be positive, okay? And if I use the same expansion as I did here, what I get is that this is equal to, so I'll do it for 1k, right? And since I want it to be greater than or bigger than 0, this implies that the trace is bigger than this. All good? So I choose a k to go from here to here. All I did is I did this substitution that we did here, right? Okay? The other thing we have to do is to show the sufficiency . We use the spectral decomposition of rho, right? Right? Since this by assumption are 0, this is 0. And the second property follows pretty much the same as before. You choose rho to be some pi L, okay? And then you check this property, pi k okay? If you expand this out, this will be the trace of pi k pi L plus delta t, the trace of pi k L pi L plus something which is of order delta t squared. If k equals L, this will be 1 plus this guy and if k is not equal to L, it will just be this guy. By assumption, this is positive, right? And this has to be trace preserving, which means that the trace, this is L and this is L, right? When k is not equal to L, by assumption, this is positive. And since it has to be trace preserving, it follows that this has to be equal to minus the sum over OK, not equal to L. And this is obviously less than 0. So we have positivity. Okay? That's it. Now, it's already an hour and a half, and I see a lot of you grogging away. Should we make it into 2 lectures? It's perfectly stop because the rest is brutal calculation. So it will take me at least an hour. So I think maybe we stop here. The important thing I want you to note is that this theorem here tells you the necessary and sufficient conditions for any L to generate a 1-parameter dynamical family of semigroup. Okay? This is what essentially we're going to use to find out the expression of this Lindbladian. Okay? So before we stop, any questions so far? Is everything clear?
Or everything unclear?
Or is nothing clear? There is this issue with the Hiller-Yoshida theorem, but it's like it would take us a lecture to prove it. So just take my word for it. Okay? Okay. Thank you.